All right. So welcome to the first session. Uh, this hopefully we will be able to finish it in around 40 minutes, and we'll start with a gentle introduction. Uh, and the goal of today is to also cover this episode, which will actually be a practical slash theory session. So once again, my name is Ashwin. I'm from Mimer, and I have my co-instructor here, Ludwiko, who will be joining in the discussion.
Yes, hello.
Hello. So the questions we are trying to answer here is what exactly is deep learning and what is a neural network? And we will be introducing some terms which make neural networks work, which are like neurons. We'll also try to understand how they actually learn. We'll also try to identify some application where it makes sense and where it doesn't make sense to use deep learning network. Um, we'll show you some of the tools. We will actually use them, of course, in the course of the lesson. And we'll also show you a common workflow. Uh, so, and this you will see soon that, and we'll try to show that the same workflow works irrespective of the task. But these are the general goals of this, the whole course actually. And so let's dive into the question, what is deep learning? So deep learning is actually just one of the techniques, one of the many techniques. It's a subset of machine learning, and machine learning in turn is a subset of AI. Although nowadays in popular science or media, it might seem like deep learning or AI has become synonymous with large language models, but it's not the case. It has never been the case. So I think if I can handpick something which is not deep learning, that would be, and machine learning, it would be something like linear regression or decision trees, if you're familiar with those things, where you use data so that a machine can understand patterns, but it's not the underlying structure is not a neural network. It's actually a function trying to optimize different parameters. Uh, is that correct, Ludwig? Do you have a better example for machine
These are
learning or deep
very
learning?
good examples. I think random forests are probably the most common, but then
Mm,
also many clustering techniques can be considered a type of machine learning that is not deep learning. Although
yeah,
then there is the foggy line of also what is machine learning itself. It's
mm,
the lines are often very blurred, right? The deep learning has a relatively clear line that separates it from the rest.
right.
Uh, because basically deep learning is anything that uses backpropagation as the
Mm,
training algorithm. But
mm,
then the other lines, what is AI versus what
right.
is not AI? When do if else finish and AI starts, right? That is
Mm,
always very, very fuzzy. There is no
mm,
well-defined
mm.
limit.
Yeah, that's a good point. Like, so the closest thing, as is written in this infographic, is they say AI is something which can sense, reason, or act like a human. And this probably is related to something which was pitched a long time ago by Turing. Like, if it behaves like a human and if we cannot tell the difference, maybe it's AI. So this is probably the connection over there. One thing which I could remember, which is not machine learning but still considered AI, is maybe one of the oldest chatbots in the 60s called Eliza. And that was not a model. It was text. It was a code which recognizes patterns in text and gave us replies, which looked very similar to a human. But that was not data driven. It was based on pure logic. Another example would be maze solving algorithms, like trying to find the optimal route to get out of a maze, can be coded without data. Um, yeah. So let's continue. So we established that, okay, if there is neural networks and if you are using back propagation, it's probably deep learning, and that's probably where we limit our discussion of the course. So neural networks, how do they look like? Uh, so it's loosely connected to how our brains work. Uh, so we try to make uh, some of these units called neurons and connect them together. And how do we organize these neurons? They come in as layers. It can be a one-dimensional layer or two-dimensional layer, as we soon see. But the simplest form is a bunch of inputs. And when we make a connection, we apply a parameter, which are called weights that you see over here. Uh, and the weights, they are multiplied as a dot product with the inputs. And then there will be usually an additional scalar, which is called a bias. So when you make a connection from some of these inputs into a neuron, it goes through all these weights. They get multiplied together, and you take the sum, and you add this bias term. And all of these are linear operations. And if we just had this much, we could have just gotten away with a single layer, and that's it. But the most important thing, probably, which gives neural networks the ability to express complex pattern, is probably the activation function at this step, because activation functions gives neural networks nonlinearity. So that's where this linear operations become nonlinear. Uh, did I miss anything, Vico?
I have two questions on this.
Yeah.
And the first one would be, do you have any sort of intuition for what is why are we doing this thing? What is the output of a neuron, of one of these things? Why, like, what is a neuron trying to do?
So what is a neuron trying to do? It's trying to, and I think it comes down in the bottom of a lesson, like when we actually try to uh, bridge together multiple connection sets. So we are trying to comprehend or detect some sort of patterns in the inputs. Uh, and also if I were to answer it, like my answer would be this activation function also tries to uh, reduce the noise and also add some complexity. But maybe you have a better answer.
What I was thinking is,
Mm,
like, because I was thinking, why do we need biases right now? Just a random thing that popped into my mind. And I was thinking, okay, but why are we doing all these operations? And I think
mm,
one easy way, in my opinion, to see it is that what we're trying to do is that we are trying to build one new feature for our data, right? So we have some data with a lot of,
mm,
let's say, inputs, with a lot of
mm,
information we have. And we're now trying to combine them to produce, let's say, a score, to produce some sort of score for this. And we will
mm,
have some inputs that contribute positively. The more input we have, the more score we have. Some input contribute negatively. The
mm,
more input we have, the lower our score will be, right? So we can do this sort of scoring.
mm.
And then we also have this sort of bias, which kind of gives us we could say a threshold, right?
You're right. Mm,
What uh, what is the threshold? So for the sum to be positive,
mm,
the values, the inputs multiplied by the corresponding weights must be above or below the threshold, depending on the sign.
mm,
So this is kind of how I see it, right? We are trying to build a score from the inputs, and we have some
mm,
sort of threshold for it. So, but it's true that it depends very much. Like there's a lot of emergent behavior that only
mm,
appears after you build a big system out of this, and that's kind of the magic of neural network. A neuron does a very simple thing, but when you
mm,
combine them together, you get a lot of emergent, complex behavior.
mm. Yeah. So yes, we will take also a look at how probably this looks like in real models somewhere in the middle of the lessons. But that's a good point. Yes, trying to find patterns and trying to get triggered. And a single neuron doesn't, maybe it's not the most interesting thing, but when you combine them, you get more interesting behavior. All right. So let's take a look at some common activation functions which are actually used. So the first one here is a sigmoid activation function. And this inherently, by the nature of how the formula behaves, it has this exponential. So it's quite smooth. But the limits of these are 0 and 1. The other activation function, which is also nonlinear, but very simple to implement, is this ReLU activation function, and we'll be using this quite a lot in this course. And this uh, avoids all negative values, will be 0 for all negative values. And for all positive values, it behaves like an identity. So it's this kink which makes this nonlinear. The third one is a linear identity or linear or identity activation function, which does nothing. Like given an input, the output will be the same. So we have a couple of questions here, and I'll put it together in HackMD as a poll, and let's see. So the question to all of you is, should I put it here? Maybe I'll put it over here. So we have a couple of options to mark. So you saw the functions, the sigmoid, the ReLU, and the linear function. So the first question is like, which function enforces the activation of a neuron between 0 and 1? And if you're on HackMD, you can mark your answer with a plus. And the lesson that we are following here is so here. So I can put that too if you don't have it. So we have a couple of votes on the plus for the first option, and yes, so sigmoid has the property of enforcing the activation to be between 0 and 1. And I think sigmoid, if I remember correctly, it's used for things like classification in classical machine learning to logistic regression, isn't it?
Yeah, that is correct.
Right. Yeah.
Although if not always, but that is the basic ones for
Hmm.
binary classification.
Right. So, and the next question is, which function would be more useful in regression tasks?
Seems we have some split voting on this one.
Yes, apparently. Yeah, so it was a bit confusing maybe because the Rayleigh also has a linear part. Uh, so usually in regression tasks, we will use a model, a hypothesis, which might be a linear function. It can be more complicated than that, but a ReLU, because it's highly nonlinear, would not be a good candidate. I think that's where it's. Uh,
I guess maybe someone could think of using a ReLU as the output of a regression if you know that
hmm.
you always that the correct answer will always be positive.
Right. Yeah.
So
Yeah.
if the model outputs something, if the output neuron outputs a negative value,
Hmm.
the ReLU will transform it into a zero.
Hmm.
So maybe that is useful, but again, if all your expected outputs are positive and your model tries to predict a negative value,
Hmm.
there might be some other underlying issue in the representation.
Yeah. Yeah. That's a good point. Yeah. So some regression task you would like to enforce is positivity. Yes. Hmm. And the third question is, which is more popular in hidden layers to introduce nonlinearity? And probably I had spoiled this already. And yes, you guys are correct. It's ReLU. It's introduces nonlinearity. And I also spoiled the first question because I mentioned classification. So yes, you can use sigmoid for classification. So maybe as it came out from this discussion, like we will be using a lot of ReLU in this lesson. It's the most simplest nonlinear activation function there is to connect some of these neural networks. As always, I mean, these are not meant to question your knowledge, so we always have the solution here, but I appreciate that you took your time to do the guesswork. Yeah. So we had established how a neuron looks like, how a connection from a neuron is through weighted sum of the weights, biases, and activation function. And when we combine multiple neurons together, they form, you can do interesting tasks. And it's the weights which determine the strength of these connections. So the weights are never fixed. They will be initialized something like a random number or empty to start with. And then on the process of training, these weights will be adjusted. So that's what we do mainly during training. So we choose some activation functions, those are prescribed, but the weights and the biases, those are the things which gets adjusted. We can also visualize a neural network as a graph, as seen below. And one way to organize these neurons, and this is not the only way, there are different ways. Like you can actually use graphs to organize neurons too in graph neural networks. But most commonly, they are organized into layers. And signals from a input layer will travel to an output layer through intermediate layers, which are sometimes hard to explain, right? We know the purpose of input layer because we know what kind of input data that we are giving. We also know probably the structure of the output layer because we have some target in mind. We want such an output to come out of a neural network. But the hidden layers, sometimes it's possible to explain them, sometimes it's not. Uh, so here we have, now that we saw, and probably the hint for this exercise is given such an list of inputs, 0, 0.5, and 1, and 3 neurons, and the weights being set to -1, -0.5, and 0.5, and a bias of 1, and use a ReLU, what would be the output of the neuron which connects all of these together? So once again, I'll put that in the document. Have it somewhere here. And you can write your answers below. So you can use anything that you have, a calculator, pen and paper, Python, if that's your jam. So yes, so we have a couple of answers, 1.25, and I think that's probably the answer if I remember correctly. So yes, the output of the neuron will be 1.25, and that's because we do this weighted sum, multiply, do a dot product of these two vectors, add this bias, and then if it's positive, you do nothing. That's what ReLU does through this max operation. So you guys are really smart, very quick to answer. But okay, let's continue. So, and this is probably alludes to what Ludwig also suggested. What makes deep learning deep learning? Like when you stack together multiple such layers together, then it has the property of like emergent properties where it can actually do interesting tasks like classifying images. But it doesn't have to be images all the time. It could be other kind of data. It can be uh, inputs to a video game. It could be uh, trying to detect different sensors from a car and trying to drive the car. So any kind of data can be in principle adapted to deep learning networks. Uh, so here are a few examples. So this is an actual network called YOLO, and this was used to detect pedestrians. And when you want to detect pedestrians, probably the input is an image, which it is here. And it is connected by convolutional neural networks. This is something that we'll discuss more in the last day of the course, how these things work. And because the image is 3D, because it has three color channels and a two-dimension in space, the layers are not, the layers are also 3D. So when you have deep networks, deep in the sense that there are many layers, you can do interesting problems. Uh, and this is also a schematic of another kind of network where it's multimodal. So it's trying to combine together images and audio in a common space and trying to find patterns. The patterns can be edge detection to start with, but maybe as you go deeper and deeper, these patterns become more. Um, let you will see probably that this some of these hidden layers might be activated to certain features, uh, and
I think,
that's probably what you meant, right, Ludwiko?
yeah, exactly. And this, I think it's really one of the most important things to understand to get an intuition for deep learning, right? The fact that a neuron takes a bunch of numbers and produces one number.
Mm,
Therefore, a layer of neurons working together takes a bunch of numbers and produces a new bunch of numbers. And what does this new bunch of number represents? It's a new way, it's a new representation of the previous bunch of numbers. It's a new representation of the same input, but it's a representation from a different point of view. It's a representation that highlights a different angle. It highlights a different kind of structure in the input. And as we progress in a deep model, what is being represented becomes more and more, I would say abstract, not really abstract, but more and more high level, right?
mm,
At the beginning, each pixel only has extremely local information. But
mm,
as you move forward, the representations that you have capture more and more larger chunks of the image, for example, in the image classification case. And therefore, they provide a more comprehensive and processed view of the input. And that is kind of the real magic, right?
Hmm. Excellent. I couldn't have described it better. Yeah. So you go from finer details to more large scale behavior of patterns.
Yes.
Uh, and then this question, like how do we neural networks learn? We describe that they are connected through weights, and we also alluded earlier in this episode that these weights get adjusted. But how does the network know where to adjust to? So to do that, we have outputs on one side, right? And when you pass data through the neural networks, all through all the weights, and finally to the output layer, which is often depicted like here to the right side, right? The outputs probably don't match. And then you have to find a way to tell the neural network how much of a big error it made. And usually this error is termed as a loss function, or sometimes in machine learning context, it's also called a cost function because it in, incurs a cost to the model. So the idea for uh, telling, communicating this error to the model is to decrease this loss. So to make such a operation, the loss functions usually has to be somewhat well behaved. Here we will do this together. And so a good example is a mean squared error, and this is probably what we'll use in the next session. A mean square error because it has this expression that uh, it takes a difference from what was the output and uh, against what should be the true output, and you square it and you make a sum of it. So by doing the square, uh, it ensures that it's always either zero or positive. And typically, uh, this kind of loss functions would have a, if it were to be one, say, single weight in x-axis, and the loss function displayed in y-axis, it would look like a parabola. To be more precise, it would have a convex behavior. Uh, this allows for the neural networks to adjust based on the weight to find where the minima is. Uh, does that make sense, Ludwiko?
Yeah.
Mm,
So at a very high level,
mm,
right? So to rephrase a little bit at a very high level,
mm.
a neural network takes a bunch of inputs and produces an output.
Yeah.
And we want the output to be a specific thing. We want to get a specific output. But the neural network, of course, will not automatically produce that output. We have to make it do that. And in order to make it do what we want, we first need to have a way to measure how wrong it is. So maybe it was a little bit implicit, but you must know already what the right answer is. If you don't know what answer you want, you cannot train a neural network. You must know
Mm,
what the answer that you want is, and then you can train it to produce that answer. And then, of
yeah.
course, then in the future, you can use it for other things for which you don't have an answer. But you must
Mm,
have first trained it on something for which you have the answer. And really, this loss function is a way to measure how wrong the model was so that you know how much the model must be changed, how much the weights must be adjusted in order to make it give the correct answer. The bigger
mm,
the error, the bigger the loss, the more you need to adjust your model. And in a sense, because the loss is the way that you judge how good the model is, in a sense, then you're acting as a teacher who decides how to grade a student, where the model is actually the student in this case. And it's up to you to a certain extent how harsh as a teacher you want to be. But all the different loss functions can have different values. But at the end of the day, you want always to reduce it. You want the model to have as little error as possible always.
Mm.
Does this make sense? It's a little bit of a rephrasing of what you were saying.
Yeah, yeah, I think it makes sense. Yes, yeah. So it's actually telling how far away you are from the correct answer.
Yes, yes.
Yeah, yeah. Uh, we will not go into how the model adjusts at this stage. This is probably a discussion for later days. Uh, but I hope you understand how an error can be imposed at the output of the neural network to tell it how to optimize. So yes, the loss function quantifies the total error, and the operation where we minimize the loss function can be termed as optimization. We will see that later. So what kind of problems are suitable for deep learning to solve? Some of these examples we have already seen in pattern recognition, like to detect cats and dogs, but to find maybe the face of a cat, which will be segmenting an image. It can be natural language translation to translate from English to Swedish or vice versa, to generate data, which is the rage nowadays, to generate text or from audio from text. So it can be all of these things, which are really hard for humans to solve, to come up with smart algorithms. There are much more examples over here. But there are also some classes of problems where it's probably not worthwhile to use deep learning. You should probably not use deep learning to do that. Uh, why would that be? It's either probably because you don't have a lot of data, because deep learning networks has the nature it is. It has to see a variety of data and large quantities to make sense. Uh, and also explainability is another challenge. Uh, as we already saw, sometimes it's possible to make sense of how these hidden layers operate, but it's just a mental model. Sometimes it doesn't work that way at all. You might imagine that certain layers detect just the eyes, just the mouth, and just the nose, but sometimes it's not the case at all. It does what it does. Uh, and then to classify things which the training data has never seen. So a network is only as good as the data, but if it's meant to perform well in a real world where it hasn't seen this, maybe sometimes it's possible, sometimes it's not. Uh, and for even if you check all these tick boxes, like you have the training data done and you don't worry too much about the explainability, and you have a specific task in mind, so you don't have to worry about going outside in the real world. It's very specialized operation. Even then, there will be simpler problems which might be possible to solve. For example, like a FISPUS problem. You can easily write a few lines of code, and that would be able to predict if a number is FIS or BUS or the number itself. Uh, or maybe image processing operations like edge detection, or maybe it's also a good scientific model which is well established and doesn't require a lesser sibling as a surrogate model. So it depends. As always, the answer is it depends. Uh, but these are some guidelines where you would like to use deep learning or you should not. Uh, and how much data do you need for deep learning? This is probably a question that we often get. What is your go-to answer, Ludwiko?
There is no good answer for this one, Ashwin, but
Mm,
as much as you can get
mm,
is typically the way I go with.
mm,
So it depends on a lot of things. So it's something that is very hard to tell ahead of time. So you
mm,
have to try out, but it depends on mostly how complex your neural network is and how hard the task you are trying to solve is.
mm,
So this is kind of the main pointers. And typically the starting point is look at existing approaches for this problem and look at how much data those require, right? If there are
mm,
already some models that do something similar. Because yeah, it's the more you need at least a certain amount of data for a certain size, for a certain model to be able to train. So
mm.
and then if you have more than that, that only helps to make the performance better.
Right. So usually the thumb rule is the more data that you have and the more information it gives to the neural network. Yeah, it's probably helpful. Yeah.
Actually, that last point is very good, is very important,
Mm,
right?
mm,
Variety of the data is
mm.
important. If
Yeah.
if your data does not match what you're trying to do, if you want to be able to predict 100 different animals, but your training data only has 50 animals in it,
Mm,
you're not going to be able to do it. So
exactly.
it's important to have every case that you want to predict must be covered by your data set.
Mm, exactly. Yeah. And there is a small comment over here, like if you don't have enough data, there are some tricks in the trade. This is commonly known as data augmentation, where you tweak and combine or rotate your data to make new data which looks different. For example, you have an image of a cat, you zoom in a bit and it looks new to the network, or you rotate the picture, you mirror it, flip it, and these are all different perspectives for a neural network. Okay, I think we switch gears here and then we try to end the session. So uh, this is the general deep learning workflow that we are going to introduce and will be following throughout the course. So what is that? Irrespective of the task, we start by formulating the problem. We try to understand what the network is trying to do. What is our input? Are we trying to classify something? Or are we trying to do some prediction based on a given input? Are we trying to predict the future state? So that's the general task. And then we look at also how the inputs and outputs look like. Whether do they need special treatment? Do they need to be transformed in some ways so that the network understands something? Something you will probably see soon is that a neural network can only understand numbers. So if it's data which looks like an image or text, probably we need to be translated to a number for it to make sense. That's how we do in the third step, where we do preparation of data. We convert our available data into numerical data sometimes. And now we are done with the data preparation part. Then you have the choice of, like Ludwika was mentioning, maybe look at others. You can, sometimes people make it open how they have done and their end results, they share it as pre-trained models. So this can be a good starting point. And this is something we will look at how to use pre-trained models in the last session of this course. Um, but sometimes it's not possible. So you're left with no option but to build a new network from the scratch so that you have the most control on. we saw what a loss function is. It's shows how far away the value, uh, the predicted value was from the true value. And we also mentioned briefly what optimization means, trying to adjust weights. Uh, Once we have set all these, we have a model ready to go, ready to ingest data. And that's the process where it consumes most of the time usually, where we train the model. Depending on how big the model is, it can be few seconds up to a few days or weeks. Uh, Once you're done with the training, it's not enough to just deploy it. We have to also see how it went. So one way to do that is to look at the loss, but we'll see more interesting ways to uh, measure the model performance. We can also do classification or prediction to make a inference step once the model is trained. Maybe you don't reach the expected performance, so you will have to find ways to refine the model. So we'll show some examples of how to refine a model. And when you're done and you want to share your results into production or to your colleagues or to publish, then we finish with the sharing step, like where we save the state of the model into a file so we can reuse it again. So
And
this is the yeah general workflow. Yeah.
yeah,
Yes.
this general workflow, I know we're a bit late, but two quick comments on this. One
Mm,
is that we will see all of these steps after the break in
mm,
practice. So you will
yes.
see an example of what it means to take each of these steps. And the other thing is that because this is a course about deep learning and what is specifically done for deep learning, we will focus on some of these steps more than others. But one important comment I want to make is that in reality, when you try to do things in a real world use case, I would say around 80% of your time will be spent in the first three steps of this process, which
Mm,
are not specific to deep learning. They are general to any machine learning or any data science project. But really, data preparation is always key. So be always careful about doing your data preparation right and spending the time on that. And in this course, maybe it will be a little bit easier because we are using data sets that are well known and we already prepared some of the data preparation code. But that is really the tricky part for the success of any project, I would say. At least this is my take, Ashwin. I don't know if what you think about this.
yeah, that's a good point. Usually, in real projects, a lot of time is consumed in the data preparation state, so it's underrated, and usually that's where you end up investing in most of your time. That's a very excellent point. Uh, so in this course, and I will not read this, this is for your own information. What we'll be using is either Pytorch, and Pytorch gives you more ability to customize. You get to see some of the internal workings of a neural network. But we also have the option, so we have prepared notebooks for you to use Keras. Keras was designed to be the user-friendly alternative to TensorFlow, but nowadays it Keras supports both PyTorch and TensorFlow. Uh, so Keras can be a really good start if you're a beginner in, excuse me, Python and trying to understand just the workflow and not interested in the nitty-gritty details. Uh, we have all of these pre-installed as we saw in previous session, and let's wrap up. We saw that machine learning is the process where we give it data and let the machine recognize patterns. We saw what neurons are, uh, how these neurons are organized in the form of layers. We also understood by now what a loss function means, and we saw some possible examples like image recognition and also how to think about the workflow that we just saw. Okay, so I think we go for a break now. And then after the break, we'll be joined by my colleague, Francesco. So we take a break for 9 minutes. So we meet again at 5 minutes after the hour.
In this session, we will try and hopefully succeed to build a neural network using either Keras or actually both Keras and Pytorch. And we will see how we describe the architecture of a neural network, so how we build the layers and connect them together, and how we train this neural network on a data set. How we can get insight into the learning process, so how the learning on a network actually proceeds, and how it performs. So I will first describe the problem, look at the data set that we're going to be using pandas and seaborn, and we will identify the inputs and outputs. Then we will do some further preparation of the data set, implement the architecture, and run the training process. And then after that, we can look a bit at how it performs. So as a reminder, today we're going through the 10 steps that Ashwin described some minutes ago. So formulation and outlining of the problem, identification of inputs and outputs, data preparation, the architecture of the neural network, training process, so loss function and optimizer. We'll see what that means. The training itself, we will actually run it. So we will perform a prediction and see how it performs. And then we're not actually going to refine it today. That will be a topic for tomorrow. And we will save it so that we can reuse it later. The idea of this episode is actually to, just get our hands dirty. So we will build a network from scratch. We will make some opinionated choices, and we will not actually describe a lot about how the neural network works on a very technical level. The idea is to come out of today saying that we managed to train a neural network with some level of performance, and then tomorrow in our session in the morning, we will understand a bit better the choices that we made and see how we can improve the performance. So what is the problem that we're looking at? We're using the Penguin dataset. It's a dataset that was published in 2020 and contains data about 3 different species of penguins on some islands in the Palmer archipelago in Antarctica. So some researchers measured a number of features related to these three different species: the chinstrap, the gentoo, and Adelie. And they measure a number of anatomical features, so the bill length and bill depth, and also the flipper length, and body mass, and the sex. So what we would like to do is to use this data, these features of the penguins, to try to see if we can predict to which species they actually belong to. So given a set of measurements, try to do some kind of prediction and see which species they belong to. And now I think I can actually stop with this and move on to the notebooks. So just for the sake of it, I will show you again how we get access to a Jupyter session and try to get there. Great. So let me share my window again. Yes. By the way, let me know if the font size is too big or too small, or if it's okay to follow. So I went back to the, Ashwin pasted the instructions, but I will go through it again. So I went to the website of the LUMI web interface, lumi.csc.fi. I will start now with Pytorch. This first part is actually the same because it will be mainly about data preparation. And then we will build a network. We will see how to do it differently in the two frameworks. But for now, we'll just show you to do it in Pytorch. So I'm clicking on the Jupyter Notebook button. Today, we actually have a reservation. So I'm picking it here. And this project should be the only project that you have access to. Then I will pick 8 CPU cores and 8 gigs of memory. This is actually a bit overshot, but should be fine. And I will take it now for 3 hours. Or actually, 3 hours is fine. And I have everything here, yes. Then I will choose basic as a type of like the settings that I'm choosing. And the version of Python will be the one Pytorch provided by CSC. And for this one, we don't actually need a virtual environment. So now I will be sure that the folder that you choose is this one. So the one containing the project number in the project folder. And I will launch it. So now my job is queued, and in a few seconds, hopefully we get access. Okay, so now I can connect to Jupyter. Oh, now, of course, my Jupyter lab already remembers what I wanted to do, but just to redo the whole thing. If you followed the instructions yesterday, you should end up, once you log in this folder, where you will find Intro Deep Learning. And then in there, yesterday, hopefully you created home folder, or your home personal folder, I meant, sorry. So mine here is Fra, and here we'll find the Git repository that you cloned. So inside there, you will find a folder called Notebooks. And now I'm going Pytorch. If you're going the Keras way, you might use the Keras one. And you will find this notebook here, number 2 classification. Okay, so we'll open the notebook and we can get started. So you will see that the headings of the sections are actually the numbers of the workflow steps that we just looked at. So just for you to know where we're sitting in that workflow. So the first part is, of course, importing what we need, the packages that we need. We're going to be using pandas. This is a library to handle data frames, so the sort of tabular data that we're going to be looking at. And Seaborn, we will use it mainly to plot things. So it's based on Matplotlib, and it's basically a statistical plotting package. So some bells and whistles for statistics plots. And then we actually booked a GPU. So we will just make sure that we're using that. So in Pytorch, to check if we're using a GPU, we use this torch.cuda.isAvailable. And this is actually, it's called CUDA, but it's vendor agnostic. So CUDA is also actually, it's what we call 2 AMD GPUs in this case, since on LUMI we have AMD GPUs. And this is basically saying if we have a GPU, then set the device that we're using to the GPU, otherwise fall back onto CPU. So if we did everything right, this should tell us that we're using a GPU, and that's what happens. So we're using this AMD Instinct. So we talked about the problem. The idea is to classify penguins based on some features, anatomical features of their bodies. And this dataset, luckily, is already available in Seaborn. So we just use the SNS load dataset, and it's called penguins. And the head method will just print the first few lines of this dataset. So there we go. We have a number of observations. This actually, so it contains the species, identified species of the penguin, which island it was observed in, and then everything anatomical. So bill length, bill depth, flipper length, the body mass, and the sex. We can use the shape just to get a look at how big it is. So we have 344 penguins on this island. And of course, we recorded 7 features for each one of them. Now, as Ashwin and Ludovico said, the 80% probably of your time in any data science project is actually spent looking at the data, exploring it, and preparing it. Then the fancier, model building part, that's actually relatively minor. But we need to make sure that we understand our data set and make some choices in the beginning of the whole workflow. So to do that, we use this Seaborn perplot function. And what it does is, given a number of features, so we have species, bill length, bill depth, and all the others, it takes pairs of each, it takes a number of pairs across this list and plots them one against each other. Maybe it's just easier if we look at it. So here we go. So basically, we have a number of plots where we plot, for example, the bill length against, well, in this case, it's just against the bill length. But then bill length against bill depth, bill length against flipper length, and body mass as well. Why do we do this? The idea is just for us to get some insight into our data. So we can see that, for example, in this case, we're coloring each data point by species. And we want to see if we can already identify some clusters, because this will give us some insight into how we should build our model. So since the final objective is for our model to understand what is orange, what is green, and what is blue, we want to understand which are the most distinctive features here. So this is actually a question that I have for you. Based on these plots, would you say that there is some class that is more easily distinguishable from the others? And given this number of plots, which couple of features will you say are the ones that are most telling? So which ones cluster better the penguins that we have among their 3 species? I will actually copy paste this in the collaborative HackMD document, and you can give me your answers. Just take 5 minutes to think about this.
Francisco,
Yes.
One of our colleagues reminded that maybe it's worthwhile to show the setup again. There are a couple of people who are struggling with it.
To show what? Sorry?
The setup instructions.
For Keras?
No, to get the Jupyter running and to have like the Git pull done.
Yes.
Yeah.
So should I start a new session?
If possible, yes.
Okay.
Why
Yeah,
not?
no.
It doesn't hurt at this stage, I think,
Yeah.
to take it slow.
Okay.
Yeah.
Okay. I will go the Pytorch route again.
Yeah, absolutely. Yeah.
Okay, so we just shut down Jupyter Lab here
Mm.
and cancel this one. Okay, so let's go again to the dashboard of the LUMI web interface. We click on Jupyter. And then for today, we have a reservation. So this is the only button that you can click, and is intro DL day 1. And the project is probably also the only project that you can choose. Then going to the resources, we can prescribe, for example, 8 CPU cores and 8 gigs of RAM. We will take 1 GPU. Someone is asking, there is no reservation, it's perfectly fine. Maybe you may have to wait a couple of minutes compared to 5 seconds, but it's perfectly fine. And here, prescribe a time. You can keep it. I think the reservation is actually, oh, it's for the day. Okay, good. You can keep 4 hours, or maybe put it also a bit shorter, since we will not be here until 2. And then the most important part, maybe it was a bit too quick before, is to make sure that when you choose the working directory here, you pick the one that contains /project/project with a project number, because otherwise you will not end up in the folder where you cloned the GitHub repository yesterday, or that we will do now as well. So this is very important. And then the Python version is Pytorch via CSC stack. And you don't need to enable any virtual environment. Then after that, you click launch. And now my job is queued. So in a few seconds, it will refresh and tell me that I can connect to Jupyter. So now that it's active, I click the blue button, connect to Jupyter. And now what happens is that Jupyter tries to be clever. So it remembers where I was, but I will close this and go back to where you should be landing, which is what the root folder here will look like, is one where you have these folders. And among these ones, you will have the intro deep learning folder. And then in there, you can create your own folder. So I will do this now again for the sake of it. So we call it FRA2, for example. And then I will open it. And then at this stage, you can clone the repository. So I open a terminal, check where I am with the pwd command. And now, since I was in this folder, I'm already in the right place. So once I'm here, I can clone the teaching material, which is on GitHub. This is deep learning info. So now here I get this folder. I hope that everyone managed to follow until this point. So I click inside, and then I go to the notebooks folder, Pytorch, classification number 2. And yes, so this is the state that we should be in now. I hope that most of you or all of you are in the right place now.
Yeah, I hope so too. Oh. But if okay, there is something to
Perfect.
record. Understood now. Good.
Oh, the classification in Keras folder, but not in Pytorch folder.
Yeah.
So if Nilam, if you cloned yesterday already, then you should do a git pull. So when you're here in your terminal, go into the intro deep learning intro folder. So this should be the full path where you're at, minus my name, of course. And there you do a git pull, and that was probably because you cloned yesterday, so you have an older version where this notebook was not there yet.
And this is probably something you have to do the beginning of every day because we are slowly adding these notebooks.
Yeah.
As we go.
So yes. So now we go back to the notebook, and I will just do it before. So import the libraries that we need. And then checking that we're using a GPU. Perfect. Then loading data sets, checking the shape, and creating these pair plots. So this is where we stopped, and this is where I asked you something about this. And I'm actually very happy to see that most of you understood what we're looking at. So the Gen 2, the green ones, they tend to be further away in almost all these combinations. So we can expect that we will have an easier time trying to predict a penguin that belongs to the Gen 2 species. And also, a few of these plots show up better separation between the classes. For example, bill length against flipper length is a very good example because we have three very clearly clustered groups, but also bill length against body mass, and up to maybe a somewhat lesser extent flipper length against bill length, and well, this is actually the same, and flipper body mass against bill depth. So this is, it looks a bit, not important, but it's actually very useful to get some kind of bird's eye view on the data set that you're dealing with, because it will help you choosing a bit better where to focus on when you build your neural network architecture. So now we go to the part that is maybe more often overlooked, but is very important to have success in your data science project, that is preparing the data. Or even before that, we should choose which are the inputs and which are the outputs of the neural network, so what we're trying to get. And we already kind of spoiled that. What we want to do is predict the class. So the output will be which species. So it will be one of these three classes. And as inputs, we want to look mainly at anatomical features. So we do not really consider the island and the sex, since they're categorical. Like we have only, 3 islands and 2 sexes here. We will use mainly continuous variables. So the bill length, bill depth, and flipper length and body mass. So as a preparation step, we get rid of these 2 columns. We use pandas.drop that basically removes 2 columns from the dataset. So we get rid of the 2 categories that are island and sex. So we see that now we have only 5 columns. And it might be the case that we see, for example, here, that we have some, not a number. That means that we have some missing values. And that could be, for example, because one penguin was, identified as a certain species, but the data regarding it was not actually recorded. And here we're choosing to drop this row. We also have other options. We can try, for example, to kind of put plausible values there. This is called imputation. We're not doing that today, but just so you know, that is a choice. So in our case, we're just dropping the not a number, that in this case mean that it's missing values. And so after dropping this, we have a bit smaller data set because we're removing all the columns that, or all the rows that have some not a number somewhere. And then we want to get only the features, right? We only want to get the inputs. So from here, we also remove the species because we want to, only get the inputs to the network. So this is the input dataset, so to say, the one that we will try to pass to our neural network after we train it. And then we need the target, so what we're trying to predict. And this is the species. So this is something that is done sometimes. And we're trying to predict one of three classes, right? So it's very hard for a neural network to predict a string that would be what we have here, because it can be one of Chinstrap, Gentoo, or Adderley. So what we do is something called one-hot encoding. This means that for it, we create three classes, so three categories that represent the three species. And since each penguin belongs to only one of those, you will have one of the corresponding species and zero in the others. Maybe it's just easier if I explained it, if I show this visually. So I'm just getting the first five columns here, or the first five rows, sorry. And we get this here. So the first penguin belongs to the Adderley, so we will have one or true for the column called Adderley and zero the two others. The second also actually all five belong to Adderley here. But the idea is that we create these columns with Boolean values or ones, zeros, so that we can use this to encode the species and to use as our categorical variables. Now, if I pick 7 randomly from there, we can see that here actually we have other species. So this one is a Gentoo, and the second one is a Chinstrap.
I think this connects to the fact that neural network only understands numbers or Boolean variables and not strings like Adderley.
Yeah, exactly.
Right. Yeah.
So yes, so this is a way to identify a species as one category. So the species here is it can be one or several categories, and to make that as easy as possible for a network to understand, we use one Boolean value for each one of those, and only set to the one of the species that we're considering in this particular moment. Then we have to do something very important. So we want to train our network. So the way that neural network training works is kind of supervised. So we show a number of examples to it and tell it, okay, given this set of features like bit length, flap length, and all the other ones that we're considering, this is a Gentoo, and this other one is an Adderley. So we show a number of examples to it. But then we also want to check the performance. So we also want to know if our neural network can actually predict something based on the training that we give to it. So something that is done pretty much always is to divide the data set into two splits that are the training and the test data set. Actually, sometimes you also have a third, but for now we can just consider training and test. So what we do is take, in this case, for example, 80% of the data and use it to train the neural network. So given the 344 that we had in the beginning, we give 80% to the network to be trained. So as examples where it knows the ground truth. So it knows to which species they belong to. And then the 20% we use to check its performance afterwards. So to have an idea if it's predicting well and where it's struggling. If, for example, there is a particular species that is struggling to classify, or in general, how it is performing. And as I said, we can also have a third split, and we would see that more tomorrow. But this is something that you will do all the time, and for that matter, is also used in classical machine learning. So even when you do a logistic regression, there's always, whenever you're trained at some kind of machine learning algorithm or deep learning algorithm, you will have the training data and the test data. And to do this, we use a kind of convenient method from scikit-learn called train test split. And this will output the features for the training. So this will be rows containing only the anatomical features that we want to give as inputs and the ground truth of those. So you'll have a line with bill length, bill width, flipper length, and body mass, and to which species it corresponds to. And then the same thing with the test. So you have both the features and the ground truth. And then we give it a number of targets. So we give it the features, so the whole data set of the anatomical features, the target, so all the ground truth, how much of this we want to keep for testing. So this is 0.2, means 20%. So we use 80 for training and 20 for testing. The random state, in this case, we give 0 because we want to, if we give it 0, then we can reproduce the results. Otherwise, there's always some shuffling involved, to something that is done often when training neural networks. And then we have this stratify parameter. This is a bit more advanced, but basically controls how the splitting is done. So this is so that when we divide the data set between training and testing, we make sure that there are roughly similar percentages in the training and in the test regarding penguin species. Maybe this is a bit convoluted. This is a way to explain this, is to say that we don't want, for example, to train the neural network accidentally only giving it example of Gen 2 penguins, and then we try to test it over Adelie, for example. We try to make sure that the distribution in the test dataset is more or less the same as the trained dataset. And this is what this stratify target is doing. And this goes back to what Ashwin was talking about a while back. So we can't expect a neural network to recognize something that it had never seen before. So we have to make sure that the test dataset is somewhat, or the trained dataset is somewhat similar to the test dataset regarding distribution. The last, so we run this and we get these two, we get these splits. The last thing that we have to do regarding data preparation is scaling. And this has to do with the fact that if we look at, for example, the bill length and bill depth, and we compare it to the body mass in grams, we see that there are a few orders of magnitudes of different. This is always in the order of tens, and the body mass is in the order of thousands. This can create problems when we're training a neural network. because what the neural network does while training is compute the error that Ashwin talked about some time ago. And it may end up that the error is dominated, for example, in this case, by the body mass. So it doesn't learn a lot the effect of the bit length, because in absolute value is a lot smaller than the body mass. So this is both really theoretical in the sense of it's very related to the fact that we have a physical error that is bigger, and also numerical, because we will be computing derivatives, we will see when we're training a neural network. And when we have such different magnitudes, this can create numerical problems. So what we want to do a lot of times is to scale the data so that they have more or less similar magnitudes. And once again, scikit-learn comes to our aid and gives us something called a robust scaler. Robust in this case means that it's robust to outliers. And what this class does is basically bring back the features to similar scales with values centered around 0. So it's just something that we do to improve the training process. And yes, so this is it regarding data preparation. As we have seen, this is pretty much independent of what we're using. There was no Keras or Pytorch involved. This is just how we feed the data in general to any deep learning framework. And I think from here, Ashwin will take over regarding building architecture.
Yes, that's the plan. So let
Yeah.
me try to set up the screen share. Hope that looks good.
Yes, perfect.
Yeah. Okay. Okay. So up until now, the steps that you're following are roughly the same. So it's at this stage, things start to differ based on which library you're choosing. So what I'll do here at this stage is to show both of it, but in the rest of this episode, we'll try to focus only on the PyTorch side of things. Since the explanation is roughly the same, you'll probably understand what is going on Keras if you are listening to the PyTorch too. So the first thing is we have the imports done already. So there's nothing to do over there. We will set the seeds for these libraries. So different libraries have their own way of setting their random number generator. And the reason why we're doing here is just because we can expect the similar results from you, so that you're not totally confused by why you get entirely different results. It might still happen though, because this is not 100% guarantee that you'll get a reproducible result. This utility is probably also useful when you are doing research, when you're changing the network, but the data remains the same, so that you're not confused whether why the data is getting better. So you're at least trying to force the same behavior. So we'll do that. I hope you understand why we set these random seeds. So let me try to pull up my notebook here over here. So I'll set my seed over here. And the next thing is to build a neural network from the scratch. So the code is given here, of course. So if you want, you can see this and type along. But I will try to do it myself so that you understand. And this is probably the most important part of this episode. So firstly, we need to set our inputs. So the input layer in Keras is done by this keras.input class. And it needs a parameter. It needs to know the number of neurons it should have. So that is determined by the training data set. The code is over here if you're wondering like what I'm typing, but of course I'll type it anyway here. So xtrain shape, and if I choose number 1, it means the number of columns that this training data set has. So that is the shape of the input layer. The concept of input layer only exists in Keras. So if you look at the Pytorch notebook, you won't see this. But at least in the Pytorch notebook, we are still trying to communicate what the input shape is. So the input layer in Keras works as a placeholder to accept the training data set. The next up is the hidden layer. So the hidden layer is what connects the input data into the first actual set of neurons. And they have their own weights to connect to. So if the way to do that is to use Keras layer.dense. In Keras, dense means it's a fully connected network. So it connects to all the previous neurons or all the previous data. That's all the connections possible. So here we will choose, and this is arbitrary, 10 neurons. And you can later on change this and see what happens. So we had roughly, what was it, 4 or something, 4 features, I think. And 10 is a good measure to choose for this hidden layer. And we also have to mention what activation layer that we want. So that is given as a parameter. We are going for the ReLU activation function. And Keras also connects back to the previous layer by doing a calling of this object that is created. So this is how we do create a layer, a fully connected layer in Keras. And to create an output layer, we do roughly the same thing. The only difference is the number of neurons in the output layer is not arbitrary anymore. Because we saw that in the previous part where we looked at the okay, maybe it's better to scroll in the notebook. So if you looked at the target data set, it has 3 columns after one hot encoding, which means that the output layer also should have 3 neurons. So in order to do that, we'll set 3. And since these Boolean variables can be represented as 0 and 1, we want the value of the output to be normalized within this range of 0 and 1. So for that, we will choose a different activation function called softmax. And softmax, and the only thing you have to remember is it's very similar to how normalization works if you do statistics. And once again, we need to connect back to the previous layer, which was the hidden layer. Now Keras knows what all the inputs and the outputs are. We tie them all together and initialize a model. Layers. That's the typo. Once the model is initialized, you can easily see how it looks like by looking at the summary. But we'll come to this in a while, and I'll show you also how this is done in Pytorch. So I have a notebook open over here, which uses Pytorch. So I come to this step. Once again, we set the seeds. We have one way for setting the seed for NumPy. In Torch, we set the seed using torch.manual seed. So that is done. And we have the examples here. So this is what we're trying to do, but I'll do this over here anyway. So there is a small typo. I've been told that it should be torch.nn.functional. So please fix that if you're on the Torch notebook. And once again, as I mentioned before, there is no input layer in Pytorch, but we have to still define the next layers, giving it information what the input shape was, how many columns or features does it expect in the training data set. So that we do as follows. We set a class attribute. We initialize usually classes in the init dunder method, as it's called. So in the init dunder method, double underscore method, or we create this layer called linear. Linear in Pytorch is exactly the same as what dense was in Keras. It's a fully connected layer, and it connects back all possible ways to the previous layer. So we tell them what was the previous number of features, the input features to start with, and the number of neurons. And we only have one hidden layer. And then we go for the output layer, which, as I mentioned before, is also a fully connected layer. So torch.nn.linear. And here it has in Pytorch how it does connections. It's not connected yet, but it has to know what the previous layer was. So if we provide 10 neurons for the hidden layer, we have to repeat the same 10 over here. And that's how it's done. So this is the number of connections it has from the previous layer. And the number of neurons for this output layer is 3 because we have one hot encoding and we have 3 species. So now these layers are defined. Now you might observe that we haven't defined the activation functions yet. So that's missing, right? So what we need to do is connect all these together. And that's done in this forward method in Pytorch. So how do you do that? We have the hidden layer. The hidden layer, whatever value of x being the training data, goes to the hidden layer first. And next it has to go through the activation function. So we do like this, f dot value x, and f is imported from here, torch.nn.functional. And the output layer, as described before, needs to be normalized. And we do that here, f dot softmax. And that's it. So, and to initialize this model, we call this class. We call the first parameter, we give the first parameter, which is the number of features that it has. Keras is a bit magical. It detects automatically what device it should load into. But in Pytorch, you have to tell it explicitly which device you want to use. So for that, you have to give this 2 once you initialize it. So once that's done, we have the models. Next step is, as we did before with Keras, is to look at the summary. And what here we use a third-party library called torch.summary. So now, and we will look at this together. The output is roughly the same for both Keras and Pytorch. So we have 50 parameters in the first hidden layer and 33 parameters in the output layer. And it's the same here too, 50 and 33. Now you might be wondering, like, why is this the case? So that's actually a question in exercise, but let's look at it together. So the reason why that happens is that if you look at the first layer, first hidden layer, it has 10 neurons, and in the input you have 4 columns, right? Which I think it's more visible here. You have 4 columns in the input. In the torch summary, they don't show that. So 4 times 10, that'll be 40. And each of the neurons will contain one bias term. So if I go back to the Pytorch explanation, so that brings the tally to 50. 4 times 10 plus 10. The same for the output layer. It's fully connected to the previous layer. So 3 times 10, that makes it 30. And plus 3 bias term, which makes the number 33. So these are the weights and biases, which together are the trainable parameters. So you'll see in the bottom of the summary saying that the total number of trainable parameters are 83. You can, of course, visualize this if you have the right dependencies as shown in this optional side quest, but we won't look at that. But it's nice to see over here. So we have 4 columns coming in. Once the dense layer is done, there is an activation, ReLU activation. And these 2 layers, the hidden layer and the output layer, are the trainable ones. I hope everything is clear until now. The next big thing that one needs to do is to choose an appropriate loss function and optimizer. So we are doing a classification task. And in the classification task, we created 3 different columns as the target. So these columns will always produce a value due to the nature of the softmax between 0 and 1. And we also have the true labels for the training data set. So the way how we can make appropriate loss function is to choose something which is known as categorical cross entropy. What it does is it compares how different these probabilities are from the true probabilities and comes up with a value which the neural network can work on. So that's the loss function for classification tasks. If you're doing something like binary classification, this is not the same. We have to use another loss function, but this works for multiple classes. And since we have multiple classes here, we'll be using that. You also need to give the neural network a mechanism to adjust the trainable parameters. We won't go into the exact process how this works, but that we'll see in the next episode how optimizer work. And as a teaser, the answer is it works through gradient descent or a variation of gradient descent. But gradient descent can be done in many ways. So what Adam Optimizer does is it tries to smoothen out how these adjustments are done. So let's take it as it is now. We'll don't delve into how optimizers work and how gradient descent works, but we'll just believe that Adam is the best choice and we'll pass that. So in Keras, you have to do that in this compile method from model. You tell them what the optimizer is as a string or as a class object, and also the loss. In Pytorch, these are different objects. So let's try to do that over here. Sorry about that. So in Pytorch, and now I'll stick just to the Pytorch notebook. We have initialized the cross entropy loss, and as an optimizer, we chose Adam. In Pytorch, we connect this to the model by giving the model parameters as a reference. So this is the way how the optimizer understand that this is the model that it needs to work with. If you're in the Keras notebook, you will observe that we can simply pass the data as it is without doing any further steps over here. And then you're good to go. You're in training mode already. But in Pytorch, you have to do something more. You have to also take care of the data you convert into the GPU device if you're using GPUs. The way that it's done is to first convert whatever this is, if it's NumPy arrays or into a torch tensor object. And when you choose either a torch dataset or a torch tensor dataset, if you go for a tensor dataset, it's easy to make pairs of the input features and the output targets. So that's what we do here. We combine this X-train, the scaled X-train, and the output target features. So the output targets. And the data loader in Pytorch, what it does is it takes this torch dataset and strains this in batches. In Keras, it does it automatically when you call the fit. The batch size is just a parameter. The default parameter is, I think, 32. But we also want to do this here for another reason, so that different batches look different. So we also pass shuffle equal to true when you're doing training. There is no magical fit method in Pytorch, so you have to do it on your own. You also need to track history on your own. The only thing Pytorch gives you is this mode, training mode, and that is done by calling this model.train method. So the training loop is just a for loop, and we iterate over the data loader. We move it to the device. Every batches are moved to the device from the CPU. We do a forward pass by passing the training input into the model, get a prediction. We compute the loss here. In this step, we do backward propagation. As I mentioned before, we'll do that later. We'll discuss how that gradient descent works and how the weights are adjusted by the optimizer. This part is only done to track history, and we add it to a list called loss. So I'll do that over here. And since it's a very small model, the result is probably very instantaneous. So we are also printing the loss. As you can see, the loss starts at a higher value, and progressively as the training progresses through epochs, different epochs, the loss comes down. One thing to note here, and this usually confused me earlier on, like what an epoch is. So in one epoch, it's not a subset of the training data. The model actually trains upon the whole data. So it sees the whole training data, maybe in a different sequence because we are doing shuffling, and also in small batches. It's the same thing over here. We train for a set number of epochs, and this is arbitrary at the moment. We'll also see how this can be improved in later episodes. So if you're on a different machine, it might take slightly longer. So I think it's good time to take another break. And keep your questions coming, if any. So please feel free to add them here. How long do you want the break, Francisco?
Do you think 10 minutes is okay?
Yeah.
We have another 40 to go. Yeah. Okay.
Okay.
Sounds good. That's you. Perfect. So now, if everything went well, you managed to train, or we tried to train a neural network. So we ran 100 epochs, where, as Ashwin said, here each epoch means going through the whole data set once. As we said also before, in Pytorch, we have to do a lot more things manually compared to Keras. There's a lot less magic going on, which means that we also needed to record the history, the training loss manually, and save it in each epoch. But now that we have this, we can plot it using Seaborn again. And we get this plot for the loss, where on the y-axis we have the loss function, and on the x-axis we have the epoch. Now, if you're doing this with Keras, this might look quite different, actually. This is due to a number of things. You can see that here it looks a lot more jittery. So it looks like, for example, we're updating too aggressively the weights. So sometimes it looks like it kind of overshoots and then it goes back again. We will see that Keras maybe does some of these things a bit differently, so it converges a bit more quickly. So in the next episode, we will actually see what are the knobs that we can tune so that we help this process go a bit faster. So there are a number of things that we can change, and it's part of our job as data scientists to, improve this. But nevertheless, it went down. So it did learn something, and we will see in the next couple of steps of the workflow where we're actually sitting. So what we can do now to check what's happening is to perform a prediction. So we take our test set and we try to predict and compare it with the true labels that we had. To do this in Pytorch, we had to prescribe a couple of things first. So first, we call this model.eval. This is a bit of a misnomer. It means that it puts the model in evaluation mode. So it does. It basically tells the model, look, now you just have to predict. There is nothing to train. So now we're just predicting. And this torch.nograd is also something that we do very often, or almost always, when we are running in pure inference. This basically tells Pytorch, you don't need to record everything that's happening to help with the training later. We just predict. You don't have to record all the steps that we're taking. And that's because we will see tomorrow that this optimizer that we called, what it does is kind of record everything that the neural network does, so it can trace back and optimize the weights based on the loss function. So this is just, it's not strictly necessary. This just makes the inference, so the prediction, faster and use less memory. what really matters is to set this eval. Otherwise, this might break the prediction. So the way that we call it is, once we set up this, we call this method and set up this context manager, is just called model that we define above with the tensor of the features in the test dataset. So if you remember, we divided our whole dataset into train and test parts. And then in the X, we have the input features, so the anatomical features. And in the Y, we have the class. So we just compute this prediction. And then we put it back into a data frame. And again, Pytorch has a lot less automation of things. So we have to take care of moving it back to the CPU. Otherwise, we cannot build a data frame out of it. So if we do this, we get the prediction that the model made about the rows that we gave to it. Now, this is numbers. This is basically the output of the softmax. So by design, that function will give us a number between 0 and 1. And we can think of this as not exactly 100% correct, but it's a very good way of thinking about this. This gives us kind of the probability that the row that we pass to it belongs to one of the species. So for example, the first row in the test dataset has some kind of 80%, so to say, chance of being Adderley. So this tells us what our model thinks. And it's a very good way of representing things because the sum of each row is 1. So we can really think of it as a percentage probability. If we want to do the same thing in Keras, once again, it's more or less the same. So we use model.predict instead of just calling the model, and then we turn it into a data frame again. So these two things look quite similar, except that, of course, since the model is different, also the predictions are a bit different. And we can go back to Pytorch because this next part about measuring performance is actually independent from the framework. As we said, this is percentages. So what we want to get as a nice output is, okay, so what is the prediction of the network actually? And to do that, we just extract from each row the maximum value. So for example, if we take row number 1, this is kind of 80%. So we're just saying, okay, it means that it thinks it's an Adderley. And same thing for row 2. For row 3, instead, the highest number is the one for Gen 2, this 90%. So we just extract the column with the highest value and say, okay, this is the prediction of the model. And if we do this, we get the list of predictions. So this is pretty much how you make predictions with this type of neural network, at least for classification. And yes, this is how it goes. Now, what we want to check is how to measure the performance. So we want to find some way of keeping track of how many times our network was right, how many times it was wrong. And this comes in different flavors, or there are different metrics that we can use to keep track of this. One of them is called the confusion metrics, and I will create one, and then we'll try to understand what it means. So once again, scikit-learn comes to our aid, and he has a very neat method to create confusion metrics. I want to stress again that this part is regarding the analysis of the performance of the network. So this doesn't really matter if we did a network in Pytorch or Keras or TensorFlow or anything else. This is just analyzing the output of the network. So you can do this in an agnostic way compared to the framework. So what we get is, first of all, the true values. So the true labels from the test dataset. And based on those and on the prediction of the neural network, we create these confusion metrics. And this one, as it is, it doesn't really tell us much. So I will plot it in a bit nicer way. So we're turning it into a data frame again to feed it to Seaborn. And let's just plot it and look at it. And it's a bit better. So what this gives is on the x-axis, the predicted label. So we get here, on the x-axis, what the neural network guessed about the data that we gave to it, and the ground truth that we got from the original data set. And what does this mean? In this case, we're saying that, for example, in the test data set, we had 30 adeles, and they were all correctly identified. So we had 30 of those, and the neural network correctly got 30 of those. For the chin strap, instead, we had 13, and they were. I'm sorry. They were. Sorry, 14 in total, 13 plus 1.
Yeah.
And the network completely missed those because 13 of those were recognized as Adeli, and one of those was recognized as Gentoo. So out of the 14 that we had in there, the neural network didn't recognize any of those as belonging to Chinstrap. For the Gentoo, instead, we're back to very good performance. So we had 25 in total, and all 25 were recognized as belonging to the Gentoo. So to make it as straightforward as possible, what we would like to have is these metrics to be diagonal, because then it means that the neural network has correctly identified each species. So we have here 30 Adeli in total, and the neural network said, okay, all 30 are Adeli, so good. In this case, we're completely off. And in the third one, we're back to the diagonal. So the gist of this is the more diagonal your matrix, confusion matrix is, the better the neural network performed. And if you think about it, this also fits up to some level with what we saw originally when we did a pair plots in Seaborn, because we saw, for example, that Gen2 was quite easy to identify. In most of the plots, it was clustered already on its own. It's a bit more mixed, of course, when it comes to the other two categories. So when it comes to classification tasks, especially categorical, all classification tasks are categorical. When it comes to classifications, the confusion matrix is a very good way of understanding what the neural network is doing, because the more diagonal it looks, the better. And it's very visually representative. So just to sum up this part, we do a prediction, and then we use the confusion matrix from scikit-learn to compare the predictions with the true values. And to make this, since it's a classification task, we take the row with the highest, or the column with the highest output as the prediction that the neural network gave. Then what came afterwards is just for it to make it plottable by Seaborn. So we just turn it into a data frame. So this is something very nice that you can do, that we will do also tomorrow to see when we improve the neural network, or when we try to tune some knobs in the neural network to see how the prediction changed. Of course, one easy way to improve this is also to try to run it for more epochs and see if it helps with convergence. But I would say this is what you might be able to check. Then today we're not refining the model, as I spoiled earlier. And that's because in the episode tomorrow, we will actually understand what all the steps that we did meant. So how does the optimizer work, and what changes between different loss functions and so on. So in the episode tomorrow, we will find out what is actually that we can control when we define a neural network, and how can that help or not to make a better network. So you can think of what you could improve in the neural network. I can tell you, for example, like I told you something already, that would be to increase the number of epochs. But maybe you could think of also of something else that we could do. For example, we define just a neural network with this hidden layer of 10 neurons. Do you think that we could do something different there? We could write it in our shared document if you want. I will leave it here, but this is more food for thought, and we can think about it more tomorrow. The last, I guess, practical thing that we have to share for you today is how to share the model. And this also means sharing in the sense of your own personal reuse. So in this case, the training was very quick, especially if you were using a GPU. They lasted just a few seconds. Training, of course, is what usually takes a lot of time for more complex architectures, and especially if you use more data than what we had today. So ideally, what you would like to do is to dump it to disk, let's save it somehow, and then just reuse it to do more predictions, more inference. And what this boils down to is generally saving the weights and biases and the architecture of the model, and then calling it back from, or like restoring it from disk, so to say, and then use it to make more predictions. So the way that we do this in Pytorch is that let's focus on this first, torch.save. This just saves all the parameters of the model, the state dictionary, as they call it. So weights and biases and a bit of the architecture. And what we did in the beginning that you might be tempted to kind of underestimate is also getting our features scaled. So if you remember, I told you before that we want something that has more or less the same magnitude across all features. And that one was also trained in a way, or is relative to the data. So we saved this one as well, because we will need to do the same treatment to the data that we want to use to predict later. And just for technical reason, we use this library called joblib that contains a piece of software that can save easily to disk this feature scaler. So this just gets saved, and you can see that I don't know where this was exactly saved now. There it is. So we have this penguins classification.pt. These are Pytorch tensors and the scalar. So what we do when we want to pull it out for later use is just create the skeleton of the model, so to say. So pre-trained model is our penguin model based on the input shape that we have, and we move it already to the GPU. So this kind of prepares the scaffolding. It just says, okay, I'm creating a model of this kind. Right now, we don't initialize any weights or anything. We just prepare the scaffolding. And then we load the state dictionary, so all the tensors, weights, and biases from the PT file that we just saved. And we do the same for the scalar. So this basically just calls it back from disk. And then the way that we do prediction with this model is exactly the same as we did before. So we put, oh, this is actually pre-trained model. So we put it again into evaluation mode because the default would be for it to be in training mode. And then we put it in a no gradient recording, and we call it exactly as we did before. So we call the model itself here after having scaled the data. And then we put it into a data frame and we print it as we did before. So this is how you reuse it for, to actually make predictions. In Keras, this is quite similar. So this whole part was the same for those of you who were following in the Keras notebook, because it was just about analyzing the predictions. To save it, once again, is slightly less involved. So we use a model.save, and thus we'll dump the model into a file, Keras. And then we reload it using keras.models.loadModel. And then the prediction, as before, is exactly the same. So we use model.predict. So in Pytorch, we have to, first instantiate the scaffolding and create the skeleton, and then load weights and biases into that. Instead, Keras does all this job for us. And yes, this is how you reuse a model that you pre-trained to do predictions or inference later.